So, welcome back to Geometry, Chapter 3. We just completed Chapter 2 about logic, conditional statements, figuring deductively, direct proofs, indirect proofs. Starting you out with a little word puzzle here. I'm not going to give you the answer, but I'll let you think about it a bit. See if you can come up with it in time for class. So chapter 3 about lines and angles, I wonder if you see anything in this picture. There are a bunch of lines and angles in there for sure. The question at the bottom, where's the 5-pointed star? I don't know if you see it or not. It's also in your book. You want me to give you the answer? Okay. So right there, you see it? 5-pointed star hiding in that picture. So in this chapter, we are going to go back to algebra a bit. I hear some groans out there, but some cheers, some algebra lovers. Some algebraic tools are used in geometry, so we're going to be looking at those. We're going to use them to help us measure line segments and angles, and look at rulers and protractors. There's going to be two postulates we have in this chapter. Remember, statements that we accept as true without proof. Ruler postulate and protractor postulate. We're going to look at relations between angles and relations between lines in this chapter. I'm suggesting that you take notes on this. Can't make you do that, but it might be a good idea for you to have notes on what we talk about in this lesson. And you look at this and you say, why do I need to bother taking notes if this is as deep as it's going to get? Let k equal to k. That in itself is a breakthrough. Do you recall that particular property there? When something is equal to itself? So here we go, some algebraic postulates. In algebra, you may have called them axioms. So these are things we just accept to be true and we don't try to prove it. There you see the one from the chalkboard, except they had k, I think it was. A equals A. Any number is equal to itself, and that just seems pretty obvious. You look at a mirror and what's in the mirror is exactly like you. Reversed maybe. Remember what that's called? Mirror is kind of a hint. That is the reflexive property of equality. And an example with numbers would be something like this: 5 equals 5, or x equals x. Second one, a plus b equals b plus a. Order doesn't matter. And that's how I remember this. Order doesn't matter when you're adding. Well, that's pretty clear. That is called the, do you remember the word for this property? The commutative property. A memory mnemonic for me is that if I start at home and I drive directly to work, that distance is going to be the same as if I start from work and drive the same route back home. So a plus b is equal to b plus a. My commute to work and back yields the same distances. So the commutative property, find a way to keep that straight. The order doesn't matter. In numbers, there would be an example. Those two sums are equal. You throw a variable in there and it doesn't matter. X plus 4 equals 4 plus x. Here's our next one. Anybody recognize that from algebra? Did anybody say distributive property? That'd be good. Do you ever wonder why it's called the distributive property? Well, a times the expression b plus c, it looks like they take the a and multiply it by b, so they distribute the a over the b and then add it to the a multiplied by the c. Distributive property. If you start this way and go back the other direction, that's something else still coming up. Distributive property in numbers. You got that one? What would that look like next? I would distribute the 5 over the sum 3 plus 2. So 5 times 3 plus 5 times 2. By the way, then that would be 15 plus 10, or 25. And why do I have this one in here? Well, you can do a lot of multiplication problems in your head if you use the distributive property. If I think of 24 as 20 plus 4, well, I know what 20 times 7 is. 2 times 7 is 14 with a 0. So that's 140. And then 4 times 7 is 28. 140 plus 100, or plus 28 is 168. So there you see it. I just divided 24 into 20 plus 4 and then used the distributive property. Here's another one coming up. Recognize this one? A plus b, that expression squared, you can write that as a squared plus 2ab plus b squared. I call it squaring a binomial. This is a binomial and you're taking it by itself and squaring it. You may have called this FOIL. Sound familiar? So it's first. I guess you'd have to write this out. Maybe I need to write that out to remind you what that would be. So it would be, come on, a plus b. Trust me, that is an a. And then times, well, if you square it, it's going to be a plus b again. So now I think you can do FOIL to that, can't you? So you take the first, a times a, and then outside, I think, what do I do then? I take a times b plus inside b times a. So that gives me 2 of those ab's. And then find the L on FOIL is the last. B times b is b squared. I just always remember that the first term here is this one squared, and the last term is this one squared, and the middle term is them multiplied by themselves times 2. Find a way to remember how to square a binomial. In numbers, can you do that one? Press pause and think about it, and then do it. So I would look at it this way. It's the same as 5 plus x times 5 plus x. You know what? I got a mess up there, so I'm going to erase this up here because what's coming is much more clear. Come on, go. There it is. So now I do that first, and then I do the last, and then I take 5 times x times 2, which then is 10x. So 25 plus 10x plus x squared. So squaring a binomial. Next one, you recognize this difference of 2 squares. A squared minus b squared. I just always remember that if you take each of these terms, do 2 parentheses, put in the first term and the second term, and put a plus, then put the first term and the second term and put a minus. This works every time. So it's factoring the difference of 2 squares, the difference, subtraction, of 2 squared numbers. Only works if you have 2 square numbers. So like this, here x is squared and we've got another number squared. That'd be 8, right? So that is a difference of 2 squares, and then how would you finish that? I would just put an x in one parenthesis and an 8, and then an x in the other parenthesis and an 8. Put a plus between one and a minus in the other. All right, so here we go now with some geometric properties. We call them postulates, or statements accepted as true without proof. So here's the first one, the commutative property of addition. So we've got a 40-degree angle, angle A, and then angle B is 50 degrees. So I could say angle A plus angle B equals 90 degrees. And in this case, it's 40 degrees plus 50 degrees is 90 degrees. Okay? What if I were to start with angle B first at 50 degrees, and then add to it angle A at 40 degrees, You say, wow, that's pretty ridiculous. It seems pretty obvious. Angle B plus angle A is 90, or 50 plus 40 is 90. So if you look at these two, it seems pretty clear that 40 plus 50 equals 50 plus 40. So A plus B, 90, equals B plus A, which is 90. Commutative property, again, from home to work, from work to home. Order doesn't matter when you're adding angle measures or segment lengths. Next is the reflexive property. Reflexive, any number is equal to itself. Here I'm going to try to give you an example that's a little bit ahead in the course. So we've got two triangles here. We have this big pink one and we have this little blue one. And later on we're going to try to prove that those two triangles, the big pink one and the little blue one, are similar to each other. To do that, we would need to show that two angles in one of the triangles, the blue one, are the same measure as two angles in the larger pink triangle. So the way we would do that is the first thing that we would say is that angle 2 is equal to angle 3. That is not the reflexive property. We just know that because those are parallel lines. They're called equal corresponding angles, but that comes later. But to get the second pair of angles equal, we're going to say that angle 1 is equal to angle 1 by the reflexive property, because angle 1 is in the blue triangle. Angle 1 is also in the pink triangle. So now we've got those two angles equal, but the point here is that angle 1 is equal to angle 1. So that's one way that we would use that. So the reflexive property. We have a little fun with the rest of these coming up here. First of all, the addition property. So if A is equal to B, then A plus C equals B plus C. Addition property. Looks like we added the same thing to both sides of the equation. Added a plus C there and a plus C there. Let's go through them all first, and then we're going to go back and look at them a bit. Here's the subtraction property. If you start with A equal to B, then it looks like they're taking a minus C from both sides. And that's always the key. If you have an equation, if you do the same thing to both sides, they're still going to be equal. Multiplication property. Again, notice how they're all starting in the same way. If A is equal to B, we've got two values equal. Then if you multiply them both by the same number, in this case C, then they're still going to be equal. The division property. Again, start with two numbers, and if you divide them both by the same number, you get the same equality. They're going to be the same. Did you notice this in here? C can't be 0. There'll be a little section in your assignments that talk about that idea, but you've heard probably, if you put a 0 in here, you're saying A divided by 0, and we have heard in the past that division by 0 is undefined. So in this particular one that you have to memorize, remember this, C can't be 0 in the division property. And then finally the substitution property. Again, if A is equal to B, you have two values equal, then A can be substituted for B in any expression. Anytime you see A, you can put in a B, or vice versa. Now let's back up just a bit, see if we can make this a little more clear. So I've got a balance here. I don't know if you can see that little fulcrum right down there, the equal sign, but a lot of times we say that equal can be represented by is balanced. Maybe you've actually done that in school before, where you put two weights there, and if they're balanced, their amounts are equal. Well, if we say then that a Mountain Dew can is equal to a Dr. Pepper, they're probably pretty close to each other. In other words, if A is equal to B, then we can add the same thing to both sides, and it still should be balanced. So that would be an example of the addition property. Let's move on, the subtraction property. Maybe you know what I'm going to do. So if these two are balanced, which we said they were, we've got A equal to B over here. Let me get my laser back. So now if I were to subtract the same amount from both sides, boy, that was fast. Let's look at that again. So if I were to subtract the same thing from both sides, you're going to go up there again? Come on. There we go. Subtraction property. A equal to B. Take the same amount from both sides, they're still equal. Okay, next. If we say that A, this side, is equal to that side, what will happen to the scale if I do this? What have I done on the left? I've taken 4 groups of those. I've multiplied it by 4. If I do the same thing on the other side here, multiply by 4, we're still going to be equal. This is the multiplication property. If A is equal to B, then A times C, in this case it was 4 of them, is going to be B times C, or 4 of them. Division property follows. If I take this whole amount as A and this whole amount as B, and they're still balanced, if I divide this into 2 groups, I get 4 in each group. And if I do the same over here, divide by the same number, I get 4 in each group again. Division property. The last one was the substitution property. And if we can accept the fact that 2 Dews and 2 Doritos is the same as a 2 liter of Coke and a Skittles, okay, we're going to call this a postulate, okay? We're going to accept it as true without proof. What can I do then? Anywhere I see one of these, I can substitute in the other. So let's go back here. Right over here, I see 2 Dews and 2 Doritos. I can substitute in the exact same, well, this, the Coke and the Skittles, because they're the same, and it'll still remain balanced equation because I substituted equal values. All right, so let's move on here now. A direct proof, remember that from last chapter. If this, then that, if this, then that, if this, then that, and so on. So it's a proof using already accepted facts, and some of those facts are going to be the postulates that we just talked about. So pretty simple direct proof. So in triangle ABC, here it is, C is 90 degrees, and B is twice as large as A. How large is A? I'm guessing some of you are figuring that out already, thinking about it. You're thinking about the triangle angle sum theorem. So you know that there has to be how many degrees there? And if we've already used up this much of that, the sum of these two you can figure out. Now somehow you got to get B twice as large as A. You notice I haven't even started the proof yet. I'm just using what we call the givens up here. This is given. They're already accepted facts. We know those are true. Plus all those postulates that we just worked with. So let's think about this. Here's our proof. In triangle ABC, angle C is 90 and B is twice as large as A. How large is angle A? So this is what we're trying to prove. So we're going to start with this. A plus B plus C is 180 degrees. And every time you make a statement, you have to have a reason for it over here. That's the nature of a proof. Why can I say this? Well, since it's a triangle, we know the triangle angle sum theorem is true. The sum of the angles of a triangle is 180 degrees. We continue. If C is 90, that was one of our givens, then angle A plus angle B plus angle 90 is equal 180 degrees. When you get to steps like this, you have to ask yourself, well, we started with this and we got to here. What changed? What's different? This step said A plus B plus C is 180. This step said A plus B plus 90 is 180. What's the difference? Pretty clear to see that where we had an angle C here before, now we have an 90 degrees. How did that happen? Well, we know that C is equal to 90. A is equal to B. So which property let us say that we can take 90 and put it in for C? Correct, the substitution property. That's our reason for being able to make this step. Now we go on. We're going to take that conclusion that we had here and make it our new what? If hypothesis correct. So if a plus b plus 90 is 180, then a plus b equals 90. So you got to say, how did I get from this to this? I always kind of mentally draw a line here, or physically on paper, say, how is the left side of the equation different on these two? How is it different? Well, it looks like they got rid of this 90 degrees, plus 90 degrees. How do you do that? You do that by subtracting 90 from the left side. Well, is that what they did on the right side? They ended up with 90. Well, sure, 180 minus 90. So the reason for this is subtraction property. We subtracted 90 from both sides. Guess how the next step is going to start? Yep, we take the conclusion here and make it the new hypothesis. If angle A plus angle B equals 90 degrees, and angle B equals 2 angle A, where in the world did that come from? That's nowhere in these steps. But it is up here in the given. Angle B is twice as large as angle A. So we've taken the previous step and a given, already accepted as true, and this given, and we're going from that to this. So again, how do you get from A plus B is 90 to A plus 2 angle A is 90? Draw that mental line and look at the left side. Draw the mental line, look at the left side. Instead of an angle B, we have 2 angle A. The right side is the same, 90 degrees, so what happened? Well, we took the fact that angle B was equal to 2 angle A's. Wherever we see angle B, we just what? Substitute it in for the angle B. So we use substitution as our reason. Continuing on. If 3 angle A is 90, and you might say, hey, where did that come from? I looked at this last conclusion here. That doesn't look, oh, yeah, 1 angle A plus 2 angle A's is 3 angle A's. Sometimes we just call that simplify. So we simplified at the end here. Now, if 3A is 90, then A is 30. How do we get from this part, from the hypothesis to the conclusion? Draw your line. 3 angle A's. Here we just have an angle A. If you can't tell what happened, try the right side. 90, 30. How do you get from 90 to 30? Well, you could subtract 60, but that doesn't work here. Oh, 3 angle A angle. It looks like I divided this by 3. The 3's would go out. And I also divided 90 by 3 and got 30. So division, each side was divided by 3. Maybe you noticed as I was going through it that each step is a conditional statement. If, then, and so on. And each step from here down starts with either the conclusion of the previous step or a given fact. So we had that. That's a postulate that we knew from before. And here's one of our givens. We came up with a new conclusion. We took that conclusion, made it the hypothesis, and came up with a new conclusion. We took that conclusion, made it a hypothesis, came up with a new conclusion, which we simplified. Oh, by the way, I misspoke. We took the conclusion and then a given from up above. We put those two things together to come up with that conclusion. Then that conclusion, we simplified a little bit. Here I'm showing you that. 3A is 90. And that became our new hypothesis, leading to final conclusion, which is an answer of what we were trying to prove. Is that the answer you had, that A had to be 30? And then B would end up having to be, of course, 60. 30 plus 60 is 90, and 90 is 180. Again, please notice this. Each step starts with either the conclusion of the previous step or a given. When you're doing proofs, this is the deal. Each step, take the conclusion from the previous and continue on with that one. Or grab a given. This one I'm just going to show you without all the fanciness there. This is what a proof would look like. They have the given at the top and they tell you prove angle A is 30. And then this is exactly what we walked through here. Okay, A plus B plus C is 180. That's the triangle angle sum. And then we took one of our givens up there and that previous step, and we substituted. We put 90 in for C. Hopefully you can see that right there. And then we took this last step and we went to here, so that was subtraction. We subtracted 90 from both sides. We continued, we took this and another given, and we ended up with substitution. We substituted in 2a. Then we took that 3a, angle A is 90, and then we divided. Each side was divided by 3. So that's a proof, a geometric proof. And we'll be doing many of those as the year goes on. So work with them. Work with them a lot now. They don't maybe start so easy, but the more you do them, you start to get the hang of it. Chapter 3, Lesson 1, I'd like to work through these. We're getting a little bit long here on our slideshow. A lot long. Well, it's an important lesson. So, Chapter 3, Lesson 1. First batch here, you're just naming the properties. So look at the first page of the lesson, or go back to the slide. Which properties are these? And again, what I'd encourage you to do is draw the line right here and see how the left side is different from the right. Or maybe just try to recognize what you're seeing there. Okay, each step, figure out the property. Okay, perimeter. Remember perimeter, the distance around a polygon. So now there's the given here is the perimeter of the green region is equal to the perimeter of the red region. The perimeters are equal. So write an expression to show this equality. Spoiler alert, please try it on your own. I've got an answer following here. Make the perimeters equal. Pause it. Okay, you're back. Hopefully yours looked like this. That A plus B plus C plus D is equal to B plus E plus F plus G. How do you get from that to this question? Why is A plus C plus D equal to E plus F plus G? Draw your line, compare the left side, compare the right side, see if you can figure out why that is the case. Why is that true? Okay, next. We've got a given, we've got two intersecting lines. They form some angles, several angles. We've only numbered 3 of them. And so now, again, he's trying to get you to apply properties from this lesson. If this, then that. So if 1 plus 2 is equal to 2 plus 3, then he thinks 1 and 3 have to be equal. Why is that? Again, look at the if, look at the then, and see what's different. Same thing here. If 1 is 2 and 2 is 3, 1 is 2, 2 is 3, then 1 is 3. It's a little bit different reason this time. 1 is 2 and 2 is 3. How do you get from this side, the if, to the then? Compare, find a property. If angle 1 is x and angle 3 is x, then angle 1 plus angle 3 is equal to 2 angle x degrees. Why is that? A little bit trickier here. We come across something a little later in this assignment. Euclid said equals added to equals are equal. These two are equal, and these two are equal. So if you take one of these and add it to one of those, should be the same as taking the other one of those added to the other one of those. So I would call this addition. Equals added to equals. Recognize this as a bisected angle. We did our arcs in there. So this figure shows how we did it with a straight edge and compass. Let's check the algebra to see that angle 1 is the size that we would expect. How large would you expect it? Well, I guess I'd expect it the same as angle 2. Or I'd expect it as half of angle A plus ABC. Let's see where they're going. If angle ABC is equal to angle 1 plus 2, and angle 1 is equal to angle 2, that's what a bisection does. It divides it into 2 equal angles. Then they think they can say angle ABC is angle 1 plus angle 1. Or 2 angle 1s. They simplified that part. Why can you go from this top line to this second line? Draw your line. Left sides are the same. Check the right side. Angle 1 plus angle 2. Here I have angle 1 plus angle 1. Oh, here's a little given. Angle 1 and 2 are equal. What property do you put there? Continuing. Now we're going to take angle ABC is 2 angle 1. That's going to be our new hypothesis here. Then angle 1 is equal to half angle ABC. Again, for your reason, look at the left side, or look at this hypothesis, look at the conclusion, look at the left side. Angle ABC is this. Then angle 1 is equal to half of angle ABC. What happened here? Got it? ABC is on the other side, but now it's times a half, and here it wasn't. Here it was 2 angle 1, and here it's angle 1. Got an answer? Write that property down. Here's what I told you earlier, trying to explain why division by 0 is undefined, that it just doesn't work. So you work through each one of these. 6 divided by 3, of course, is, yeah, and the reason is, question marks have to be the same number. Do the same thing here. Try to get the same number in for the question mark. Same thing here. See, we've got some zeros here. There's a 0 there and a 0 there. Oh, and there's 2 zeros. Put the same number in for the question mark. And now they ask one question. What's strange about the equations in exercise 16? What's strange there? I would have rather asked another question. I'm going to ask it now. What's strange about number 14? This is our division by 0, isn't it? What answer do you want to put in there? Can you put a 0 in there? You'd say, well, no, you can't. Because if that's a 0, this has to be a 0. And it's pretty clear 0 times 0 is not 6. Matter of fact, you can't put anything in for that question mark to make it work. That's why division by 0 is undefined. Is that the same down here? 0 divided by 6? Well, let's try it. What's 0 divided by 6? Well, if you have nothing and divide it into 6 parts, you're going to have 0 in each part. Can I take that 0 over here and put it in for this question mark and still have a true multiplication? Sure I can. 6 times 0 is 0. Let's move on. Here's that common notions I mentioned a little bit earlier in the slideshow. He had 5 of them, and one of them is this. If equals are added to equals, the wholes are equal. Equals added to equals are equal. So here's what it looked like. His other book, by the way, had this in as a property. So if A and B are equal and C and D are equal, if I take A and add it to C, and I take B and add it to D, it's got to be equal. I could have taken A and added it to D, and that'd be equal to B added to C. I'm going to do a little proof of that here. Follow closely because then you use that same idea on a similar one. So if A is equal to B is given, we say that A plus C is equal to B plus C. Why can I do that? Again, look at the hypothesis, look at the conclusion. What's the difference between them? To see the difference, draw your line here. On the left, I just had an A. On the left here, I had A plus C. They added C on that side. Did they do the same to the other side? Sure they did. So I would call that the addition property. If A plus C equals B plus C, and C is equal to D, that was up here in our given, they think they can say that A plus C is equal to B plus D. Well, how is the hypothesis different from the conclusion? Draw your line through the equal sign. Here I have A plus C. Oh, and over here I have A plus C. So nothing happened on that left side. Let's try the right side. Here I had B plus C. Now I have B plus D. Somehow the C turned into the D. Yeah, right there. That's convenient. If C is equal to D, you can substitute either one of them in for the other. So where there's a C, I can put the D in there, and so I get this line. So that'd be substitution. Here's what I said would happen. You're supposed to do the exact same thing with the division problem. So follow the pattern on number 18 and come up with it. Try it on your own first, okay? I think I've got it laid out here for you. So try it. So A is equal to B and C is equal to D, and neither of them are equal to 0. That's all given. So this is the way we do a proof. What's the next step going to be? If I'm starting with A equals B and I want to get here, well, I'm going to say A divided by C equals B divided by C. Well, that's pretty easy. Division by C. I divided both sides by C, which I can do because C is not equal to 0. We said that. We're almost there, aren't we? If we're trying to get to A over C is B over D, and we're at A over C equals B over C, we're really close. We just have to get that D changed to a C. And we can do that right away because we were given way up here that C is equal to D. So I'm going to use substitution to put it in for that C to get D there. So substitution. Okay, here's an algebra problem that maybe one of you did in class last year, maybe Algebra 1. And we use these two reasons. There's a mistake. What mistake was made? Can you see it? So here's the same thing. Logical thinking helps find and fix such errors. So let's suppose, like we had here, that x is 13. Let's suppose x is 13. If it is, if 2x plus 7 equals 19 and x is 13, so these are our givens. We had this and we have this. Then we could say 2 times 13 plus 7 is 19. Why? What is our postulate that we're using? Well, what's different? 2x plus 7, 213 plus 7. Well, we must have just substituted. If 2 times 13 plus 7 equals 19, this previous conclusion, then 26 plus 7 is 19. How do you go from this hypothesis to this conclusion? You could call it multiplication, but it's better to just say simplify in this case. If 26 plus 7 is 19, then 33 equals 19. Okay, again, we're just simplifying. We're putting these two together. We're not looking for an answer yet. This contradicts the fact that 33 is clearly not 19. Therefore, our assumption that x is 13 is wrong. It doesn't give us the correct answer, but we do know that it's wrong. The question is, what kind of proof does that sound like? We suppose something, we came up with a contradiction. Set 2, we've got a right triangle in here, and we've got some crescents off of those legs of that right triangle. We're given this. We don't debate it. It's just given to us. That Roman numeral 1 plus 2 plus 4 plus 5, in other words, all these semicircles on the legs, their area, they say, is the same as 2 plus 3 plus 4. In other words, this one big semicircle here. That's kind of weird. That those two added together to those two equals just this one big semicircle. What can you conclude about how the total area shaded by the light blue compares with the area shaded by the dark blue? And at first blush, you look at that and say, well, I don't know. But use your given and use the properties that you have. Can you find in this equation the light blue areas and the dark blue areas? Well, it's Roman 1, Roman V, and 3. Do you see those in the equation? I see Roman 1, I see Roman 2. Oops, I don't need 2. 1 and V, and then I see Roman 3. So what's in there? What else is in there? I need to save these two. Hold it, this one and this one. And I need to save this one. Does that give you an idea of what you're going to be doing? Which property would help you determine the relation between those two and that one. Here's my hint. I'm not going to give you an answer, but what can you do? Moving on. Geometry to solve a algebra issue. So if you look, we've got the given. It tells us we have one large square divided into two smaller squares and two rectangles. It looks like the rectangles must be the same size. They're A long and B wide. So some questions. What are the areas of the two smaller squares? Well, they're squares, so you know how to find the area. Here we go. What is the total area of the two rectangles? Spoiler alert, okay. Try it yourself. It's a rectangle, so it's length times width. And there are two of them. So the answer, AB plus A times B is 2 ABs. How long is each side of the entire figure? Well, it's a square, so it looks like each side is A plus B. Probably should have said, make sure you pause, because I'm going kind of fast here. We're running kind of long. Write an expression for the area of the entire figure. First of all, in terms of the length of its sides. So this whole figure, what would be the area of this whole figure? Got it? Well, it's A plus B times A plus B, or, hey, you're squaring a binomial. Use your FOIL there. Or maybe just do this. A plus B expression squared. So we just simplified it. How about the expression for the whole area in terms of the areas of the four parts? Well, we've got them up here. We've got the two squares and we have the rectangle. So just add those together. Does that look familiar? So write an expression to indicate that these two expressions are equal, this one and this one. So just write an equation. Make them equal. So A plus B expression squared is A squared plus 2AB plus B squared. Look like FOIL? That's exactly what it is. But here geometry demonstrates why that works out. Going to China 1607, page from their book, and it looks a lot like which theorem? So here we break it down a little bit, and this gets complicated, okay? I'll tell you that right off the bat. These are givens, that the area of triangle ABC, this little triangle in here, is equal to the area of triangle CDE, this little triangle in there. That's just a given. Doesn't matter why, don't worry about that. That the area of the yellow square is 2 times the area of triangle ABC, and that the area of the yellow rectangle, this guy here, is 2 times the area of triangle CDE right there. Now at this point, I don't know that the picture helps me very much because I just look at this. Area of triangle ABC, so here we have triangle ABC, here we have triangle CDE, here we have the yellow square, here we have triangle ABC, but it's times 2. Here we have the yellow rectangle, and here we have the triangle CDE again, but it's 2 times that. Well, triangle CDE is there, and it's also there. Well, what else do we have? Another part says that the red square area is equal to the area of the red rectangle over here. So we have 4 givens, and we're supposed to use those and the properties to try to figure out why each of the conclusions is true. So I'm going to let you work on that a little bit. Area of the yellow square, so go up here, here's the yellow square, and 2 times the area of triangle CDE. Well, we know the area of the yellow square is 2 times the area of triangle ABC, but this wants triangle CDE. What lets you do that? Next, the area of the yellow square, I see that right here, right up here. Let's go back to the laser. Right up there is the yellow square, equal to the area of the yellow rectangle. Well, how do you get that? Area of the yellow square. The yellow square is 2 times the area of ABC. Oh, here's the area of ABC is area of CDE. Maybe that helps. Okay. And the rectangle is 2 times the area of triangle CDE. So find 2 of those to put them together to help you get 33. Next, the area of the yellow square plus the area of the red square. Well, we know the red square and the red rectangle are the same. So if you look at 33, and then look at this given right here, you can get 34. And finally, what's the theorem that this is trying to demonstrate? We're getting there, hang in there. So here's the equation we know for area of a circle. Area is pi times radius squared. They're telling us there's another formula, and they ask you to develop it by show your method and use some postulates that we have from today. Did you like this from the quadratic formula from algebra? Here it is. What's the hypothesis of this theorem? Now they give you some of the steps. Maybe you remember these. You're supposed to give the reason. How can I go from the if to the then? Draw a line through the equation, the equal sign. How is the left side different from the right? And figure out what postulate lets you do that. Same thing on 39. Same thing on 40. Find the postulates that fit. And what kind of a proof starts like that? If this, then that. If this, then that. If this, then that. Now we go on to the next step. Trying to solve this equation. And they always gave you what A, B, and C were, and then you tried to solve it. What postulate is being used when you go from this guy and these givens to this guy? Now they ask you to flash back to algebra and simplify it to find x. Suppose I should give you a little spoiler alert. Try it if you want to. See what you can come up with. I've got the answers coming here. And I always like to show step by step what I do. So first I substituted in, hint, hint. Then I started to simplify, squared the 5, multiplied out these terms, multiplied the denominator. And then I subtracted 25 from 24 to get the square root of 1. So we have negative 5 plus or minus 1. Plus or minus 1 over 4. So that's negative 4 over 4 when you use it as positive 1. And if you use it as negative 1, what happens? That's negative 6 over 4, which is negative 3 over 2. Okay, getting into some of the sticky credit here, but there's a pi. They agreed it was the largest pi they'd ever seen. Dilku was so impressed that he decided to figure out its circumference in feet. He used the wrong expression. He used the expression for area, but he got the right answer. 3 good questions about how that could possibly have happened, and then find the area. Again, spoiler alert, please try it on your own, okay? Don't work through what I have. I do have this. Under which conditions would this work? Namely, that the area and the circumference measure the same. That the area and the circumference measure the same. I wish I didn't have them here, but I did. So don't look if you want to challenge yourself. Or don't listen. And here's the set 3. Kind of a little riddle, and see if you can find out the mistake in here. All right. Wow, that was a long one. 50 minutes. Hopefully it helped you, but I'm sure there'll be some questions. So go ahead and bring those questions